Welcome to the second video in Motion. In this video we'll look again at the relationships between displacement, velocity and acceleration. So in the previous video we saw that if we were given displacement we could differentiate to get to velocity and differentiate again to get to acceleration. And in this video we'll look at the reverse. So if we're given acceleration, how we get to velocity or displacement. So if we start with the relationship between displacement and velocity, we know that if we have a constant velocity, then it's equal to the displacement divided by the time. So if we're just rearranging that, we can, with a constant velocity, it's very easy for us to find the displacement. It's just how fast we were moving times how long we were moving for. But what if we have a velocity that's changing over the time period that we're interested in? So in this case, we have a velocity that's constantly increasing over the time. So we can't use our equation for constant velocity. But what we do then is we break up our time period into small parts over which we know the velocity is constant. So if we make our delta t in this case small enough, we can approximate that our velocity over that little delta t is constant, and then we can use our constant velocity equation to calculate the displacement for that tiny little time. And we can do that for each little time period. And then we know that our total displacement over our time is equal to the sum of all of our small displacements. And once we know that, we can see from our graph that if we sum up all these little displacements, actually what we're looking at is the area under the curve. And in this curve, that's quite nice because we can divide our area under this curve into a rectangle and a triangle, and we know how to calculate the areas of each of those. So for the rectangle, we've got base times height, which is v0 times t. And for our triangle, we've got half base height, which is half times t, and then our height is the difference between the initial and final velocities, so v minus v0. I've highlighted this equation just because it's one of the equations for motion, and we'll see it again later on. But so what do we do now if we've got a changing velocity, but it's not such a nice curve? So if we've got this curve, trying to calculate the area under this curve is not particularly straightforward. So in this case, we approach it the same way. We divide our time period of interest into tiny little blocks over which we can say the velocity is constant, and we can calculate then the displacement for each of these little time periods. Once again, our displacement is equal to the sum of all of these little ones, and we can write that as a sum. And then if we write that, we know that the displacement is equal to the velocity times the time. And if we make our tiny little time periods small enough, then we just convert our sum into an integral. So to get from, if we're given acceleration or we're given velocity, then to get to velocity or displacement, we just need to integrate. So if we're given acceleration, the integral of acceleration over the time is the velocity, or if we're given the velocity, then the integral over the time is the displacement.